Thank you, John, for being with us today at the March meeting Quantum Machines booth. We were discussing just now how passionate you seem when you speak to people about physics and about Qolab, your recently made companies. I just wanted to start. This is the first time I can hear it from the source. I heard about Qolab, I read about it, but this is the first time I can speak to you. So I want to take a little bit, a step back. Give me a historical perspective. What's the story behind Qolab, and how did you come around to build your own company?
Well, the story really starts way back in 1980s in graduate school, where we actually built the first qubit. It was actually prehistoric qubit. It hadn't been invented yet. But we were working on superconducting devices to show that we can see quantum behavior in it. And what was very different at the time is we came up with the idea that you can do spectroscopy and see the energy level transitions, which of course is a very clear signature of quantum mechanics. Yeah. So that was really great, and we showed that, and it was a great thesis project. And just thinking back to that time, it's kind of amazing to see what's happening here with all the different hardware.
Wild.
Yeah, so for example, for that experiment, I had to make my own coax, for the dilution refrigerator. You could buy copper coax, but you couldn't buy copper nickel coax. So we made our own coax, and we had to find attenuators that worked. So it was all very basic. And then from that, I basically worked on quantum devices the whole time. We did some more experiments, quantum experiments at Scalable. I went to NIST and built electron counters. And then in kind of the mid to late 1990s, these funding became available for looking at qubit research. So I started doing that at NIST and had some good results. And then UCSB was interested, and I could start a really focused group there at UC Santa Barbara. And basically, I was wanting to build a quantum computer where we were just playing around with how you would build it and how to make good qubits. The big moment was when we started understanding how the surface code worked.
Okay.
And I understood how error correction would work, and I could kind of picture this in my mind. And it really focused what we had to build.
So it came from the high level, actually, like thinking about, how would you actually run something interesting?
That's right, because there were general ideas in the Steam code and other things like that. And I'm very much, if anyone's ever read Peter Thiel's book, 0 to 1, it's on startups. And it talks about a definite optimist versus an indefinite optimist. Most people are indefinite optimists. Oh, let's do some research here and see what happens. I like to have a real plan. I like to have a definite goal. And that's what I liked about quantum computing, is that, you're making a qubit. It has to be a good qubit. So what's your T1, T2? How do you couple them together? And then when we did the surface code, it's like, oh, I see what the architecture is. And since it's it's a grid, that's something you can build on a chip.
Yeah.
So at that point, it got very focused. I actually wrote a paper it's very highly cited. There's not much new in the paper, other than I did a high school statistics calculation on what the error rates would be, so you can understand it.
Yes.
But it's mostly Andrew Cleland who wrote the paper. Excellent. And what was, I think it made a big change in the field, because then people could understand for the first time, the ordinary person, not the surface code theorist, on how it worked. So then we had a really concerted thing what to do. We did some experiments at UCSB, and then Google decided to build a quantum computer. So they talked to me, and it made sense for us to go there. And then they had the resources and the ability to hire all my students and other people to really focus on building the quantum computer. And that ended up with the quantum supremacy experiment in 2019, which is really the culmination of, 6 or 7 years of thought on what to build. And that was really great. Afterwards, the Google group decided to kind of change their management structure and the way they were doing things. I didn't feel I felt in. I felt it wasn't just really didn't make sense to me anymore.
Yeah.
So then when I was on my own, I started thinking about, well, what is it that you really have to do to build a quantum computer? I started talking with Alan Ho, and then we came up with both a technical plan, which I talked about here, with the wafer scale integration and other things. With Alan, it was more the business plan of how we want to collaborate with semiconductor companies, your company, other thing. And then we brought in Robert McDermott, who had done some beautiful experiments on how to scale up the measurement. Yes. So all this stuff came together, and we were able to.
You really managed to, focus a mastermind of a team. It's really incredible.
And it was interesting because we were in a startup. We didn't have any constraints on what to do, and we had to do a lot of thinking and reading and calculating. But we felt very fortunate we were able to come up with a plan. We sat on that for a couple of years, which was hard. But with the paper we published a few months ago, and now here we're kind of talking about it. And we got a good reception. I'm really happy about that.
Yeah. I really like this method of yours of following a plan, or at least making sure that you can make a plan. Because it kind of narrows down the things that you actually need to do. It makes it actionable in some sense.
Yeah, and what's interesting is people come up and say, what if we were to do this, or what if we were to do that? And I have to explain, the plan there is get you started, you know what you're building. But it's totally fine to pivot, especially as a startup company.
Yes, of course.
If there's a better way to do it, let's talk, and maybe we can do that. And that actually happened here at the meeting. We talked to someone who had some interesting idea, and I think we'll follow up a little bit on that.
Okay, very nice.
And we have to try things out.
Of course, and let the researchers in us, blow some steam and try different things.
Yeah, but I'm pretty difficult about saying if something's going to work or not going to work.
Yes, it's very...
Okay, so you have to be really focused on the system engineering and the long-term vision, but there's clearly some ideas that can help us.
Let's talk a little bit about Qolab specifically. You have shown here the APS March meeting, the plan for Qolab, and what kind of... tell us a little bit about it. What is... I guess what I'm asking is, how are you different? Let's say, how is your approach different at Collab?
So first of all, on the technical side, we have a plan to scale up that, I can think about in my mind, and I can see how you could put together. I can see it in my mind.
Yeah.
But the elements in there are a little bit tricky, and there's a lot of things we have to develop. But working with the semiconductor industry, this is things they already know how to do, or is going to be a stretch, but you can imagine that it can be done.
Yeah.
So on the technical side, that's important. But just as important is there's a business plan here too.
Of course. Yeah.
And the business plan, what most groups are doing now is they're trying to do everything themselves.
Yeah.
And you look at IBM, Google, Rigetti to some degree, it's called a vertical integration where they're doing everything. Yes. And if you think about the semiconductor industry, this is how, let's say, IBM was in the 50s, 60s, 70s. They did everything. And then in the 70s and 80s, you had Intel, you had all these other companies starting to build the individual components.
Yes.
And then it went horizontal, where people specialized and made it better and made it cheaper. And that really brought forward the computer industry.
Yes. Yeah.
So think of in the business organization is very horizontal, where we have, companies, and we have startups, and we have government labs, we have universities, in the kind of organization, but we also have people starting at the bottom of the stack at the hardware. Let's say Synopsys doing design. We've talked about NVIDIA working with them, you guys working with them. At the top end, we have Hewlett-Packard Enterprise, who makes supercomputers. Yes. And putting all that together, we then have a nice horizontal stack.
Yes.
And we think doing all that is going to be very possible. Now, I think there's a reason why it wasn't done before, and that's because we had to learn more. But for example, in the fabrication after doing fabrication for several decades now, we now know enough to talk to the people at Applied Materials
I see.
and say, okay, this is our model. Okay, we're not sure about everything, but we know enough to say this is what we want to do.
Yeah.
They come back to us and say, yeah, we can improve this step and this step and this step, and we go back and forth and we can come up with a plan.
Yes.
And let's say 10 years ago, I don't think I could have done that.
Yeah, so it's a little bit about knowing enough to have a reasonable conversation with people with different backgrounds or in a different field.
Yeah.
But you have set up Qolab in a way that this is already the standard for you. You're
That's right.
already, building collaborations and you're not trying to specialize in every aspect of the stack.
Exactly, and we're going to specialize in what we think is the most critical thing of building the good qubit chips.
Okay.
And that's what we're focused on, and we don't have to worry about other things.
Exactly.
But for example, for the control circuit, we've worked with you to specify what we need.
Yes.
And we're using their machines and stress testing them and getting it to work.
Yes.
And then we're feeding back on things that we need to work on, and you're getting back to us really quickly. And this is a very efficient way to work.
Yeah.
When you have the right companies and the right discussion, then everything's working right.
Yes, yes.
And the same thing's happening with Applied Materials and all the other companies.
So what role does, since you mentioned the control system, what role does the control electronics play, in the stack?
Well, you have the qubits and the dilution refrigerator kind of thing, and then coming out of that, we have the control system. And the control system is both the hardware and the noise and the specs and all that, which in fact, we're working on to systematize measuring that a little bit more, because that's so important. And then on top of that, you have the firmware and whatever, immediate software stack, which again, you guys are working on.
Yeah.
And when I was at UC Santa Barbara, I built my own hardware. I built the FPGA code.
Yes.
The students who are good at software built a stack.
Yeah.
And we continued that at Google, and that was great. But I don't need to do it again, and I'd rather leave it to the professional engineers and software developers.
Yeah, it's also a matter of specialization, right?
The key is that we can talk about it, and I can tell about my expertise, and then we can work together to put together a
find the right
system.
way to
and in the end, it's about building a good system.
Yes.
And it's a system engineering.
Yeah, I think we are pretty much aligned on not only on the vision, but also on what is the goal that what are we trying to achieve.
But I would say, the best part is that with, your team is working with my team, and I'm not involved in that. Lord, they're communicating well. We're having meetings all the time. We're solving problems, and that has to be done.
Yeah, it's amazing.
But for example, at kind of the hardware level, we're discovering that the local laboratory noise environment is really important. So we've done things to understand that, to kind of explain that so people can do that, equipment to buy, how to measure that properly. So, and that's something you're going to use.
Yeah.
So, we're developing some of that infrastructure so that we can build it well, you can know the specs are, and then when we sell to customers, they can check out their lab and clean up their lab noise environment in order to make really good qubits.
So what progress do we need to make, especially on the control side, let's say in the next 5 years? What do you envision the challenges of control will be?
I'm just going to say, I'm a practical person. So in the next 6 months, we have to work with our good qubits and your good qubit, your good control system, and make sure we're measuring everything optimally.
Yes.
And then a little bit longer time scale, make sure that we can automate that so that someone can use the software, use our hardware, and bring up a qubit with minimal intervention. Because right now, my analogy here is right now you're kind of a race car driver.
Yes.
Okay, and we want it to be at least, driving my Toyota.
Yes.
Okay, and maybe, self-driving if we can, but probably not fully self-driving.
So making things simpler,
but at the same time, these are complicated qubits, so you have to built into the intelligence to deal with that.
Yeah.
But we need to do that well. And the thing is, you have to do that at 1 or 2 or 5 qubits do that really well, because if you start scaling up to a lot of qubits right away, you quickly get lost. And this is what happened, years ago when I was doing it at UC and Google, is, we found, that you can get really lost if you don't have good code and you aren't doing it systematically. And going to Google, because the emphasis on the software engineering, everyone stepped up and they really enable things to do better.
Yeah.
And I think if we have better hardware, then the software will be a little bit more stable and easy and reliable to use too. So I think that's going to be better.
So,
but okay, that's the next year or whatever.
Yes, yeah.
But going longer term, we're going to want to start scaling up, and we're going to be looking to you to make hardware that's cheaper.
Yes.
Okay, so we can scale up.
So reducing the, let's say, price per qubit, increasing density of channels.
Yeah, increasing density, and and then we'll know a little bit more what the exact specifications can be.
Yes.
So we kind of know that now, but we have to do some good testing on that, which goes into the whole system design.
Yeah.
And then, we continue doing that, and then eventually what we need to do is turn these modules into an ASIC chip.
Yes.
To really now, that's going to be hard and whatever, but that way we can make it cheaply, and then we can integrate thousands or hundreds of thousands into our things. And the baseline plan right now is to put those chips at 300 Kelvin and cool them properly, of course. And then we
are going cryogenic with the compound.
Well, okay, you start with the chips at 300 Kelvin, and then you have a flex circuit board going down to low temperature, which you can mass produce, okay?
Yeah.
And, and whatever. And then, depending on the power dissipation of the ASICs, you can then decide what temperature you can put it at, matching that with your cryogenics.
Yeah, it depends on the cooling power at that stage.
So what I like to do is say, we have, kind of an existence proof, at least cryogenically. And then you say, okay, if you hit these certain targets, then we can do things in a better way.
Yeah, sort of a tier goal approach.
Right. Now, of course, we'd like to put it at 3 Kelvin. Yeah. Putting it at 10 millikelvin is too hard. We'd like to put it at 3 Kelvin. If we can do that, that's great.
Yeah.
But if we can't, it's not like, the project is not going to work.
Yes.
We can do that.
So,
but I'm going to say, building an ASIC chip is not trivial.
No, not trivial at all.
But I think it's within. Look at your cell phone. I mean, this has.
It worked before.
Yeah, people know how to do this. We just have to figure it out how to do it properly.
So our work for the next, let's say, few years is to really increase performance, increase scale, reduce cost, and then eventually narrow down on what the exact specifications need to be in order for us to be able to move to ASICs.
Yeah, that's exactly the way I'm thinking. And of course, we have to see with all the engineering constraints, what is it you really want to do, and that just takes some work.
Yes.
But in the beginning, we just have to get it to work well, and we have to know why, and we need to know how to specify, because to know whether your electronics works well, we should not have to connect it up to a dilution refrigerator.
I see.
We have to do that so many times in so many ways, and to have all the noise metrics, and not on mostly on our side of the room and whatever. Yeah. We have to understand that, so
it's
we
sort
know
of a validation problem.
Yeah, but you want to know that the airplane you're going to build is always going to fly, right? Okay, so it's as simple
kind of
as
an
that.
important metric.
Yeah, it's an important metric. Yes. And I think people kind of know how to do that now, but we have to bring the engineering discipline to that. And
some system engineering approach.
Yeah, and what's interesting is if you talk to people who do fabrication, they're all about doing things with the 99.999 percent fidelity. So us having our foot in that door is really good, because it forces us to think, okay, how do we do that? And of course, real products have to do that. And you have to understand the physics.
Yes.
And I actually think there's a lot of physics in figuring out how to do all this.
Also interesting physics.
Interesting physics, and then we have to be able to communicate it properly.
Yes.
So, as a professor, scientist, I really like this.
Yes.
It's more engineering, but it's for a good cause to build a quantum
technological
computer.
problems are still interesting
Yeah,
to
they're still
solve
interesting and valuable.
and large puzzles to solve.
And I actually think from the business case, I think our knowledge on how to do that is going to be really important. And then your knowledge on how to build that, working together, can make a very compelling case.
So on the qubit side, we discussed a bit what is the role of control today and what we hope for the next few years. On the qubit side, what does Collab offer today, and what do you see this going in the next few years?
Right now, we can offer resonator chips as a kind of test if your system's working right, and we can put it in mount. We also have single qubits, 6 on a chip, where people can test, and this is 100 to 200 microsecond T1 flux tunable qubits. They're really pretty good. And then we have in test right now a 2 qubit coupler, which we have to iterate on and get to work. But that looks pretty good. And we're building this. We've solved some real problems. We're building this so that it can be very good 2 qubit gate.
Okay.
So when we've done the design work, the intrinsic errors, that's without worrying about T1, is 10 to the minus 5, 10 to the minus 6, and they're fast gates. And then when you put them in a 2D array, the intrinsic errors are going to be about 10 to the minus 4. And then with the T1 at 150 microseconds, it'll be 99.5%.
We're talking about
like
errors on individual 2 qubit gates.
Yeah, on individual 2 qubit gates.
Okay, what is the bottleneck there? What do you think?
Well, we just think that we came up with a good design, and we have some novel ideas on how to do that. And then, of course, you have to make good qubits.
Yes.
And then the biggest bottleneck is these are paper qubits that I'm telling you about.
Okay.
We have to measure it. Okay.
Yes.
But we made the qubit. It looks pretty. It's not perfect yet, but we have to play around with that. And I'm very encouraged. There's other groups who are getting hero 2 qubit gates below 10 to the minus 3. So people are doing that. We have a plan to do that too that we're very excited about. So. We just have to do that.
So it sounds like the next months, if not years of work for Collab, it's really on operational fidelity. Like fidelity of gates,
the qubits get better, make the gates better, and then, make it in a reliable, scalable way with the tried materials process.
Yes.
And we just want to show that we can, crank out, and what we want to show is 2 qubit gates on 10 qubits and show the distribution and not just talk about the hero.
Yes.
Now, I think we can get to, let's say, 3 times 10 to the minus 4 average fidelity, something like that. Average fidelity, okay, on paper, but they're plugging in numbers. We have to demonstrate that. And, at that point, I think it'd be, very interesting product.
Yes. On what scale will this become useful in your mind when you envision the future of Collab?
This goes in a little bit of in our business strategy. We think that even single qubit gates, tunable qubits with single qubit fidelities, 10 to the minus 4, and then 2 qubit qubits with in the 10 to the minus 4 range, maybe a few more qubits, 4 qubits. Given that they're really good qubits, and researchers can have opportunity to use that. That's kind of an interesting thing. In particular, they'll get access to pulse level control through your system. So we think that's kind of an interesting thing for, let's say, educational groups or something. Okay, and then we scale up to make bigger and bigger. But let's say if we make a 32 qubit array with super low error rates on all the qubits. That's around 3 times 10 to the minus 4. That's really interesting from some algorithms point of view.
Yes. Okay. If you were to bet today on what algorithm will be the first to be successful in showing some progress.
I'm not an expert on this, but I think with the device we're thinking of making, you can probably do fermionic simulation
Fermions.
at 32 qubits to kind of test ideas in quantum chemistry. It's still analog,
Yes.
but we're thinking about a device that's kind of mapped to that problem.
Yes.
But there's other problems people can map
Yes,
to do.
yes.
But I would just say, for the educational, just to have access to a machine with low-level control, with really good qubits, playing around with different ideas on control, there's a lot to do there.
Yes. Yes.
And I think it would help us and help,
Of course, it will help also train the next generation of physicists.
And I would say, my own bias, of course it's very biased, is that's going to help us build a useful quantum computer to really understand good control, very low error control, than having large error rates on 50 qubits.
Yes.
That's nice. People are doing it. Google's done it for many years.
Yes.
I did it. Okay, but really figuring out how to make very good qubits and operate and control them in a realistic way.
Yes.
This changes things.
Yes, it's also a very refreshing point of view because nowadays you hear a lot about ultra large systems, thousands of qubits, and also you hear about the applications that might be accessed thanks to these very large systems. But I hear you saying we also need very good qubits at the small scale. We need to be able to understand them, to train people.
And the point is if you have a large scale system with high errors, you can't run a big algorithm.
Yes.
Okay, 100 qubits with 1% error.
Yes.
One, clock cycle, instruction set.
Yeah.
You have of order 1 error.
Order 1. Yeah.
So maybe it's a couple instruction sets deep. Okay. There's some things you can kind of play around with.
Yes.
But if you want to go deep, you want to go big, you have to make the qubits better. If you want to do error correction, you have to do the qubits better. So, I've done the scaling of the qubits thing. I was very happy. And now I'm stepping back and saying, let's really focus on good qubits, but making them in a scalable way. And my hope is once we get a few qubits and we understand what we're doing, then we know how to engineer big systems, and then we can do that rapidly.
Yes, so it's wider and deeper circuits thanks to
and then
qubits
we can build those
performing.
systems and build it in a way that's scalable. And the other thing that really no one talks about is, we're all physicists, is cost.
Yes. Cost, of course.
And we have to bring the cost down. Now, we already talked about we need to bring the cost
for
down
the control system.
of the control circuits, and you all understand that, we understand that. And the same thing for the qubits and all the other components we need to do. Because if we want to really build this into an industry, it can't be $10 billion per quantum computer. Okay, that's not going to work. So we have to bring that down. And again, working with all these different semiconductor companies, they know how to manufacture, they know how to do the engineering right. We're trying to design something based on manufacturable components.
Yes, you're really taking a kind of a system engineering approach to this.
Right.
It's making the right choices at the small scale, really understanding the physics deeply enough to be able to be confident on your qubits even before you start thinking about scale. It's a very, I think, to me, it's a very refreshing perspective, and you're also clearly very passionate about what you do, and I want to really thank you for this conversation because it's really enjoyable to hear you talk about your work. We discussed plans, the plans for Qolab. You're really focused on making plans, which is amazing to see, and it's really evident.
We're thinking about what's the 5 and 10 years it's going to look like, and what do we have to do if this is long-term goal.
Yes. So is there anything else from Qolab that you want us to hear?
No, that it's just been really fun in your own startup, and Alan and Robert and I are working really hard to think about our culture.
Yes.
And we're for me, I'm looking at what SpaceX did. We can be a little bit gentler than Elon Musk, maybe, but the culture of really trying to build something ambitious and grand, and really focusing on good ideas.
Yes.
We like thinking about that and trying to build a company.
You
that
really
way.
have this ability of combining the educational approach with
Yeah.
the sort of a business orientation.
And
let's
that's
say.
what I'm learning, and that's what's
Yes.
really fun.
It's,
Because you have to combine, and I think that's what Elon Musk has been able to do with
Yes.
SpaceX. He actually has someone else running the business end,
Yes.
which makes it even better. But yeah, combining that too, because in the end, we're all getting funded because it's a potential of doing something very economically viable.
Of course.
And that's what we want to think about as we build up our company.
I'm looking forward to see what happens at Qolab in the next few months or years.
Great.
Thank you, John.
Yeah,
for
thank you. It's been really fun.
spending some time with me. Thank you.